In this podcast, we'll be looking at two different optical phenomena that give us evidence of light behaving as a wave. And the first one is called Young's double-slit experiment. In this experiment, we start with laser light, and that laser light is coherent, meaning that all of the waves are in phase. So we have crests and troughs, and again, all of the waves are in phase. It's very organized. Then what we're going to do is we're going to send this laser light through two thin slits. And the thin slits have a width that is smaller than the wavelength of the light. We're going to project that image onto a screen, and the distance between the slits and the screen is called L. So here we've got D is the slit separation, and L is the distance to the screen. We should also note that since this is laser light, we know the wavelength of the light, and it's coherent, again meaning that all of the waves are in phase. Now let's think about what we've learned from having 2 point sources. When we have 2 point sources of light, what we end up with is this pattern of circular wavefronts. Now we also know what happens when the circular wavefronts overlap. When we have crests overlapping, we get constructive interference. And I'll draw dots here on top of points of constructive interference. And what we can see is that we'll get these patterns, these lines of constructive interference. And then between the lines of constructive interference, we get destructive interference. And the way that this shows up on the screen is as a pattern. We'll get a pattern of light and dark, what we call fringes. So this is a fringe, and basically what it is a bright spot. And it's a place where we have constructive interference of light. And the reasoning is that if light shows this property of constructive interference, then light is behaving as a wave. Now, there's some fancy geometry that goes along with this, and it has to do with similar triangles. But essentially, what we can do is we can come up with formulas for to find the location of the constructive and destructive interference. And the formulas are based on which fringe we are on, and these variables of slit separation, distance to screen, and wavelength. So when these wave fronts, or when these bright spots are created, the central one is called the central fringe. And we number it as fringe M equals 0. And then when we go out one fringe up and one fringe down, we number those the first fringe, M1, M1. And then if I go out another fringe, I'm going to number that M2, M2, and so on. So this would be M, my third fringe out. So essentially what we see in terms of the geometry of the situation is that constructive interference we can write a formula that says that d sine theta is equal to m times the wavelength. In other words, d, which is the distance between the slits, times the sine of this little angle in here, is equal to whichever fringe you're on times the wavelength. And then we'll see destructive interference every half wavelength. So for destructive interference, d sine theta equals m plus a half times the wavelength. If we turn the page, here's a better diagram. So here I've got the two slits separated by distance d. I've got the distance to the screen as L. I've got my fringes numbered here. I've got the m equals 0 as my central maximum. And then fringe 1, fringe 2, and then going in the other direction I've got them numbered -1, -2, and so on. And the distance between the central maximum and a given fringe will be equal to m, that's your fringe number, times lambda, that's the wavelength of the laser light, times L, that's your distance between the slits and the screen, over D, where D is the distance between the slits. Let's take a look at how we could use this information to solve an AP question. This comes from the 2009 AP test, the B version. This is question number 6. In a classroom demonstration, a beam of coherent light of wavelength 550 nanometers is incident perpendicularly on a pair of slits. Each slit has a width of W of 1.2 times 10 to the negative 6th meters, and the distance between the centers of the slits is 1.8 times 10 to the negative 5th meters. The class observes light and dark fringes on a screen that is a distance L of 2.2 meters from the slits. Your notebook shows the following setup for the demonstration. And here's a diagram just like the diagrams I've already shown you. A says calculate the frequency of the light. Well, they give us that the wavelength is 550 nanometers. That's 550 times 10 to the negative 9th meters. We know that the speed of light is 3 times 10 to the 8th meters per second. So I can use frequency times wavelength equals velocity to solve this. Essentially, I'm going to take 3 times 10 to the 8th and I'm going to divide by the wavelength, and I end up with the frequency being 5.5 times 10 to the 14th hertz. B, calculate the distance between two adjacent dark fringes on the screen. Well, the easiest two fringes to work with in this case would be fringe 0 and fringe 1. If I find the distance between fringe 0 and fringe 1, that is the distance between any two adjacent fringes. So I'm going to choose an m value of 1 for the first fringe. And I know that that distance is m times lambda times L over D. So again, I decided I'm going to use the first fringe as the distance between the central maximum and the first fringe. The wavelength is 550 nanometers. That's 550 times 10 to the negative 9th. The distance between the slits in the screen is given at 2.2 meters. And the distance between the slits is 1.8 times 10 to the negative 5th. So now I solve this, and I get 0.067 meters. The entire apparatus is now immersed in a transparent fluid having an index of refraction of 1.4. C, what is the frequency of the light in the transparent fluid? Well, frequency doesn't change, so it's the same as A. It's 5.5 times 10 to the 14th hertz. D, does the distance between the dark fringes increase, decrease, or remain the same? So let's go back to our formula. The distance between the fringes was m lambda L over D. Now, what happens to lambda when we increase the index of refraction? We know that the index of refraction is related to speed. So we know that the speed of light in a substance is equal to speed of light in a vacuum divided by n. And we also know that this holds for wavelengths as well. So if I take the wavelength in a vacuum and divide by n, that will give me the wavelength of light in a substance. So in this case, what we've done here is we've increased the index of refraction. If I increase the index of refraction, that will decrease my wavelength, and if I decrease my wavelength, that will decrease my distance between fringes. So the answer is decrease.